Class 12th Chemistry, Alcohols, Phenols and Ethers, and the topic which we are going to discuss in this video is chemical reactions of alcohols and phenols, and subtopics are acidity of alcohols and phenols and esterification. Alcohols react both as nucleophiles and electrophiles. Now let us see how. The bond between OH is broken when alcohol reacts as nucleophiles. Now you can say if this bond is broken, then this oxygen will acquire the partial negative charge. That means this oxygen will act as a nucleophile. Okay, and it can attack with this electrophile and product can be formed. The bond between CO is broken when they react as electrophiles. Okay, and protonated alcohols act as electrophiles. Now let us see again. This is alcohol, and as we know, this OH has two lone pair of electron. That's why this proton, that is H plus, can attack on this oxygen, and we will get this one. This is called protonated alcohol. Okay, now in this protonated alcohol, this carbon, actually this oxygen is more electronegative. That's why this bonded pair of electron will shift to this, and this will acquire the partial positive charge, and that's why this is electrophile, and nucleophile can attack easily on this carbon. Okay, that's why reaction of alcohols can be classified into two categories: reaction involving cleavage of OH bond and reaction involving cleavage of CO bond. Okay, in this video we will discuss the reactions involving cleavage of OH bond. These are the reactions involving cleavage of OH bond. And these reactions verify the acidity of alcohols and phenols. First of all, reaction with metals. Alcohols and phenols react with active metals such as sodium, potassium and aluminium to yield corresponding alkoxide and phenoxide and hydrogen. Okay, that is, alcohol will give alkoxide and hydrogen, and phenol will give phenoxide and hydrogen. You can see these equations. This is alcohol when react with the sodium. This is RONA. This is sodium alkoxide along with the liberation of hydrogen gas. This is tertiary butyl alcohol. When react with the aluminium, we will get this aluminium tertiary butoxide along with the liberation of hydrogen gas. When phenol react with the sodium, it will form sodium phenoxide with the liberation of hydrogen gas. Okay. Phenols react with aqueous sodium hydroxide to form sodium phenoxide. This reaction, phenol react with the NaOH, then this will form sodium phenoxide. Okay. These reactions show that alcohols and phenols are acidic in nature. Again remember, this reaction, that is reaction with sodium hydroxide, is not shown by alcohols. That's why we can say phenols are stronger acid than alcohols. Okay, and in fact, alcohols and phenols are Bronsted acids. Now, what are these Bronsted acids? That is the substance which donate a proton. Okay, donate a proton. Proton donors are known as Bronsted acids, and these alcohols and phenols can donate a proton to a stronger base, and if this is represented as B, you can say this is base, this is alcohol which is acidic in nature, and when this proton is donated to this base will convert into its conjugate acid BH, and this alcohol which is acidic in nature, after donating this proton, this will convert into its conjugate base alkoxide ion. Okay. The acidic character of alcohol is due to the polar nature of OH bond. Actually, in this case, this is more electronegative. That's why this will acquire partial negative charge and this will acquire partial positive charge. That's why this bond is polar. And due to this polarity, alcohols are acidic in nature. An electron releasing group like alkyl groups, methyl, ethyl, that is groups showing positive inductive effect, increases electron density on oxygen and decreases the polarity of OH bond. We can say presence of these groups increase the electron density on this oxygen. That's why its negative charge becomes less, and that's why it has the less tendency to attract this bonded pair of electron towards itself. This result in the decrease in polarity. When polarity decreases, this decreases the acid strength. And for this reason, the acid strength of alcohols decreases in the following order. We can say that is primary alcohol, which have only one alkyl group, are most acidic. Okay, and tertiary alcohols, which are having three alkyl groups, least acidic. Is it clear? This is the decreasing order of acidic strength of alcohols. Primary alcohols are most acidic, secondary are lesser, and tertiary are least acidic. Reason is due to the plus I effect of alkyl groups. An electron withdrawing group, that is minus I effect group, decreases electron density on oxygen and increases polarity of OH bond, and this increases the acid strength. Alcohols are weaker acids than water. How can we prove it that alcohols are weaker acid than water? This can be illustrated by the reaction of water with an alkoxide. You can say this is alkoxide ion and this is water. In this case, this water has the tendency to proton this one. Okay, that's why we can say water is better proton donor, and better proton donor means stronger acid than alcohol. Then this water, after donating proton, this will convert into conjugate base hydroxide ion. Okay, and this alkoxide ion, which is accepting proton, and this will convert into alcohol, which is its conjugate acid. When this alkoxide ion is a stronger base, then this conjugate acid, that is alcohol, is a weaker acid. This we have discussed in the class 11th. Okay. An alkoxide ion is a better proton acceptor than hydroxide ion. That's why we can say alkoxides are stronger bases. Sodium ethoxide is a stronger base than sodium hydroxide. Now, alcohols act as Bronsted bases also. Whatever the reactions we have discussed, these reactions represent that alcohols are Bronsted acids, that is proton donor. But at the same time, alcohols can also act as Bronsted bases. Why? Because this is due to the presence of unshared electron pairs on oxygen, which makes them proton acceptor. On the oxygen atom, two lone pair of electrons are there, and that's why this oxygen can accept proton, and alcohols may act as Bronsted bases also. Now, acidity of phenols. The reaction of phenol with metals, for example sodium, aluminium, and sodium hydroxide, indicate its acidic nature. But the reaction of phenol with aqueous sodium hydroxide indicates that phenols are stronger acids than alcohols and water. Now, what are the reasons? There are three reasons. First one is the hydroxyl group in phenol is directly attached to the sp2 hybridized carbon. As we know, in phenol, that is benzene, OH is attached to the benzene ring. The carbon of benzene ring is sp2 hybridized, and sp2 hybrid carbon is more electronegative. Hence, OH bond in phenols is more polar. It results in an increase in ionization of phenols than that of alcohols. Okay. Second reason, Due to resonance in phenols, the oxygen of OH group acquires positive charge, which results in more polarity of OH bond. You can see these are the resonating structure. Now see these three structures. In this oxygen acquired the positive charge, and due to this positive charge, this OH bond becomes more polar. Because this partially positively charged oxygen has the tendency to attract the shared peroxyplectron towards itself. That's why this bond becomes more polar. More polarity of OH bond, more stronger the acid. Third reason is phenoxide ion formed after ionization is stable due to resonance. And we can say in this resonance, delocalization of negative charge is taking place, while no resonance in alkoxide ion. Now you can see this reaction. This is alcohol. After giving this proton, this will convert into alkoxide ion, and this will not show any resonance. This is phenol. After giving this proton, it will form this phenoxide ion, and this phenoxide ion, see, these are the resonating structure of phenoxide ion. That's why we can say phenoxide ion is more stable than phenol. We can also say that is phenol also showing the resonating structure. Then why these phenoxide ions are more stable than phenol? You can see these resonating structure. In these resonating structure of phenol, there is separation of charge is taking place. You can say this is positive charge and this is negative charge. This is positive charge, this is negative charge. This is positive and this is negative. This is separation of charge. Okay. While in this phenoxide ion, separation of charge is not there. Already negative charge is there, and this negative charge is delocalized. Okay, and that's why we can say although there is also charge delocalization in phenol, its resonance structure have charge separation, due to which the phenol molecule is less stable than phenoxide ion. Okay. Now, effect of substituents on acid strength of phenols. In substituted phenols, the presence of electron withdrawing group, that is groups having negative inductive effect such as nitro group, enhance the acidic strength of phenol. This effect is more pronounced when such a group is present at ortho and para position. It is due to the effective delocalization of a negative charge in phenoxide ion when substituent is at ortho or para position. On the other hand, electron releasing group, that is groups having plus I effect such as alkyl groups, do not favor the formation of phenoxide ion, resulting in decrease in acid strength. Now see one example. This is orthocresol. In orthocresol, this CH3 group, this has plus I effect. Okay, and this is phenol, and this is orthonitrophenol. This NO2 group has minus I effect, and due to this NO2 group, the phenoxide ion formed from this is more stable, because due to minus I effect, more delocalization of negative charge is taking place. While in case of due to plus I effect of this, concentration of negative charge is taking place. That's why it will not stabilize the phenoxide ion, and this will stabilize the phenoxide ion. That's why this orthonitrophenol is most acidic among these three, and orthocresol is the least acidic. Okay. Now these acidic strength can be expressed in terms of pKa values. Now what are these pKa values? Now if you remembered Ka, this is called acid dissociation constant. Okay, and negative log of this, that is minus log of Ka. This negative log of Ka, that is known as pKa. As we know, higher the value of Ka, stronger the acid. When Ka is higher, pKa will be lower. Okay, that's why we can say any acid which has lower pKa value is stronger acid. Now just see the values. Orthonitrophenol, this is 7.2. Phenol, this is 10. This is orthoglycerol, 10.2. This is ethanol, this is 15.9. Now again you can compare, that is, this is phenol and this is ethanol. Phenol is million times more acidic than ethanol. Okay, and we can say orthonitrophenol is more acidic than phenol and orthoglycerol. Now let us see one example. Arrange the following compounds in increasing order of their acid strength. Now summarize whatever we have discussed. Phenols are more acidic than alcohols. Is it clear? And in phenols, if plus I group is attached, it decreases the acid strength, and if minus I group is attached, it increases the acidic strength. Okay, now let us see. This is propane 1-ol, 2,4,6 trinitrophenol, this is 3-nitrophenol, this is 3,5-dinitrophenol, this is phenol, and this is 4-methyl phenol. Now out of these compounds, this propane 1-ol is alcohol. That's why it is least acidic. Okay. Now in this 4-methyl phenol, methyl group is present, which has plus I effect. That's why this is less acidic compared to phenol. Okay, and after that phenol. Now in all these three, this is what in this nitro group is present, but in this 3-nitrophenol, 1 nitro group is there. In 3,5-dinitrophenol, 2 nitro groups are there, and this 2,4,6 trinitrophenol, 3 nitro groups are present. More the minus I effect groups are present, more acidic strength is there. That's why this 2,4,6 trinitrophenol is most acidic. Okay. Esterification. Alcohols and phenols react with carboxylic acid, acid chlorides, and acid anhydrides to form esters. Like this is ROH is alcohol and AROH is phenol. When this react with the carboxylic acid, esters are formed. Now what are these esters? That is RCOO and this is R dash. Okay, now this R or it may be AR, and this group COO, this is ester group. Again this when alcohol or phenols react with. Now what is this? This is acid anhydride. Again we will get the ester. This is again alcohol and phenol react with the acid chloride. This is acid chloride in the presence of pyridine. Again we will get the ester. All these reactions represent the esterification. Now the reaction with carboxylic acid and acid anhydride is carried out in the presence of a small amount of concentrated sulfuric acid. Okay. The reaction is reversible, therefore water is removed as soon as it is formed. Now see first two reactions, this one and this one. These are the reversible reaction. That's why as soon as this water is formed in this reaction, and we can say in this reaction as soon as this carboxylic acid is formed, it should be removed to get the more amount of ester. The reaction with acid chloride is carried out in presence of base, that is pyridine. This is the acid chloride. We are taking this base pyridine. Why? Because this HCl is stronger acid and this is neutralized by this pyridine, which is basic in nature. To neutralize HCl, which is formed during the reaction, it shifts the equilibrium to the right hand side. Acetylation. The introduction of acetyl group, this CS3CO group, this is called acetyl group, in alcohols or phenols is known as acetylation. And acetylation of salicylic acid produces aspirin. Now see, this is salicylic acid. Okay, we can say this is 2-hydroxybenzoic acid. When this reacts with the acetic anhydride, this is acetic anhydride, then we will get this acetyl salicylic acid and this is known as aspirin. Okay, and the CH3COOH is produced. I think you are familiar with this name, aspirin. This is one medicine. Okay, and this aspirin is used for pain relief, and any medicine which is used for pain relief, that is known as analgesic. And to bring down a higher temperature of body in case of fever, such type of medicines are known as antipyretic. That's why we can say aspirin is used as analgesic as well as antipyretic. Okay, thank you.